approximation and estimation of scale functions for spectrally negative Lévy process. It's a recent paper. So basically, this paper was authored by Haruka, Irie, and Yuki. That was 2024 paper. So basically, my outline will follow. So basically, I'm going to follow the introduction, the main problem that was addressed in the paper, the research question that was considered, and then the proof, which is the main result. So this paper connects three ideas, which are the spectrally negative Lévy processes, connects the scale functions, and their applications. Henry's theory and exit problems. So because the spectrally negative Lévy processes allows for downward jumps, it is very useful in insurance, right? Where it actually helps premiums to be accumulated continuously. And also claims, okay, has sudden downward jumps. And then for the scale function, we know that it is denoted by and can be defined through a Laplace transform as the integral of 0 to infinity e negative. And so why? And then so that is my introduction. And then we come to why this is a major problem that the writers of the. Okay, so the implicit nature of the Laplace transform suggests to us that in most cases there is no explicit formula for computing the scale function. And so because there is no explicit formula to do that, we have most applications in Rick's theory, or most quantities in Rick's theory, depend on the scale function because the scale function is extremely powerful and is central to the application. And so quantities such as the real probabilities, the discounted latent time, and exit probabilities all depend on the skill function. And so they take the form of the implicit nature of it, but we are unable to compute it numerically. And so the authors of the paper, that is Horashi and Lévy, proposed. So that brings us to the research questions we first considered. And so you consider the research questions that can we construct a sequence of functions that can approximate skill functions accurately. This is the question. And so depending on the question, can we construct a sequence of functions that approximates skill functions accurately? And so the authors proposed that we represent the skill functions using an orthogonal polynomial sequence of functions. And so this was the proposal. And then the idea is what they proposed, and I'll prove right here. And so all we are basically doing is that we are trying to look for an explicit formula for the implicit nature of the skill function, so that it will be able to be used in the field, like where the room probabilities and insurance companies will make good use of it. And so once again, we define the implicit nature. We are 0 to infinity, negative theta x. And we would want to expand the skill function, and by doing so, we have where ln of x are the Laguerre polynomials. But you may be wondering, why would the authors use the Laguerre polynomials, right? And so I will come back. The Laguerre polynomials form an interval on 0 to infinity. They are compatible with exponential weights, and they simplify Laplace type integrals. That's why they consider the Laguerre polynomial. And so after expanding this skill function, we then want to substitute the expansion into the Laplace transform. And interchange the sums. Which gives the integral 0 to infinity e minus theta. It just becomes minus a new variable is introduced, x. this can be rewritten as but over here, we would use the key Laguerre identity. Alright, what is the key Laguerre identity? The key Laguerre identity.
So are you supposed to have like the x somewhere?
Yeah, thank you. This is the key Laguerre identity, and so we're going to employ it. And so it becomes integral from 0 to infinity. So we can let z to be equal to theta 1, theta plus 1. Then we can see the 1 over theta plus 1 is actually 1 minus z. That's when we subtract this from 1. And so it becomes integral 0 to infinity e minus theta plus 1. Which is equal to 1 minus z summation n equal to 0 to infinity. And so when we increase, we can have this now becomes 1 over sine theta plus 1 minus k equal to 1 minus z and equal to 0 to sine infinity.